It's a slightly different talk, not so much about methods, more about where we try to use the methods on the industrial scale size. So my name is Alexander Karl. Ron Bates sits in the audience. I'm from Indianapolis, USA. I think he sits up in Derby, so not so far away from here. So first a little talk about Rolls-Royce, a few words. So we are not doing cars anymore, so that's a different company now. So because typically we are doing a lot of engineering, so we are an engineering focused company and focusing on power systems and propulsion systems. And that's not just gas turbines. So what do I mean with engineering company? So we have around 16,000 engineers worldwide. That's the engineering subfunction. So the rest of the company is manufacturing and then production and so on. Overall it's over 30,000 people, but quite a bit of the people are engineers. You can see the distribution there, so there's some electrical engineers, design engineering is kind of the biggest one. We spend around 1.3 billion in research and development every year. We have, as you probably know, a lot of university technology centers. Quite a few of them are here located in the UK. So what are we doing? So these are all products which we do. You probably know us for the gas turbines. If you fly around here, you get a lot of that. So, but now I think we do the hybrid electric trains, and they're actually, I think, trialed out here in the UK. So it's a diesel electric power pack for trains, so that you can cruise into the station on electric power, no noise, no pollution. And then when you're on the countryside, you can use your diesel. We do a lot of ships, whole system integration and so on. You can pollute the countryside and not the station. So there's deep understanding of materials, electronics, data management and services. We do have a whole services business. As you probably know, the business model is more along the lines of selling services and not selling engines. So there's how do you maintain the engines, what's happening to the engines in the field. That's where a lot of data and stuff comes in. That's where the statistics comes in. That's where the math comes in. That's where all the methods come in to analyze all that data. So what else? So what are we doing in the design phase? So most of our design starts off with some analytics, and you called it earlier finite elements, I think, is one of the analytical methods. So we do CFD methods and so on. And we apply these methods to various components. So we start off with component simulations. Over here there is a fan. So we put one of these fan blades and we try to model that. Now there's different physics coming in. So there's the temperatures on the fan blade. That's not too bad. It's right at the front of the engine. It's fairly cold. If you go to the back of the engine, the turbine blade, it operates actually at temperatures which are above the melting point of the metal. So you need to do something with thermals to keep it alive. It's like a London double-decker bus pulling on the structure when it runs. And we have 70 of these double-decker buses pulling on the structure. So there's a lot of stress in the structure, so you need to do stress modeling. Then you have all the data about materials, life modeling, and so on. On the fan, we have other problems. You throw typically birds at these fans, the front bit, so you need to do tests about that a fan can survive such a bird strike. So you can see one little picture down here. I think I have a pointer. That might make it easier. So there you throw birds on it. These things are vibrating. So and we have all these disciplines which we need to connect to get an answer, is that component fit for purpose? And that's the component. So now we have one blade here and one fan. Then we need to integrate that fan into a subsystem. Then the casings come along and so on. So you need to do a subsystem simulation, and then you integrate that component in a whole engine, which we call a virtual engine simulation. And you actually can do nowadays with the tools, at least the CFD run we can do thermomechanical runs of that whole structure in transient thermomechanical runs to predict temperatures and stresses throughout that structure. So, and then we go to our friends from Airbus, and they integrate that piece in their piece. So, and that's the picture we are sitting in there. One of the key things, if you do these simulations, is how you organize them, because they all interrelated, these simulations. So you really need to think about, how do I go from my requirements, which are very vague typically and very high level, down to my detailed 3D simulation finite element analysis. So the previous talks were talking about how do we solve a problem down here, but that gets integrated up here. And we have uncertainties down here, but at each level we have uncertainties. So we need to deal with that. How do we go from that big system down to that small detailed system, and how do we take care of the uncertainties? That whole chain and hierarchy of integrated models is informed by test data, manufacturing data, service data. And just typically we get lots of data points, gigabytes of data per day coming into the company from our service areas and so on. So that data needs to be analyzed, needs to be related to these. There could be data for the parameters you were talking earlier about, and so on. And how does it all link with the modeling world? And in this case, I'm not using the modeling from that. It's probably more the simulation type stuff. So building these simulations. There's probably around 60 years of design knowledge, people who know how to design these things. It's not that easy, and the tools are not yet ready, I think, to really completely do a gas turbine in a computer. There's so many unknowns, uncertainties, that one run wouldn't give you the right answer. It will give you a wrong answer, and you don't know how wrong you are. So you need to have your experience and so on. So that's all needed to be integrated in a consistent way. So this is just some of the big problem points we have and where we are working and so on. Any problem, so we can do simulations on here and do the uncertainty stuff. We can do simulations down here. For each of these simulations we do, when we talk about uncertainty, we use a kind of structured process. So, and that structured process starts with actually understanding your inputs. So what is driving your design? What are your geometric parameters? What parameters are influencing your design? So we group them typically in what we call noise factors and control factors. These are things you decide about. These are things you cannot decide about, you're uncertain about. Earlier you talked about, what was it, viscosity, which is a parameter in your Navier-Stokes equations. You don't exactly know what it is, and your result will change depending what parameter you choose. So that would be a typical one up here. You cannot influence it, but it's uncertain. Your geometric dimensions, they will be down here. So you try to get a hold of that for each of the problems. After you've done that, you can then take all these parameters and you need to find the data. And you need to analyze the data. You need to make sense out of the data. So there is things like that whole IMR chart, statistical modeling of the data. There's then material characterization, and then there's service observations. If you look, there's a plane hidden in that dust here. So I have a bigger picture a little bit later. So that's typically very difficult to model and get data for. So, but that's the operational behavior of our products. So if we understood all these design inputs and we have data, we then use typically standard statistical methods to analyze them. So you get all these data, you look at it, you basically try to identify distributions if you can for your input parameters, always the uncertainties, box plots, just standard distributions. One of the biggest problems we start to see is the correlation stuff. All these inputs are typically not independent. So now what are you doing with Monte Carlo if you have non-independent input parameters? The sampling is not that easy anymore. So you need to pay attention to these correlations in your data sets. And if you have a lot of data, you will get a lot of correlations, and these covariance matrices are getting really, really big. There's a lot of terms in these covariance matrices. So if we use these kind of things, so we get identify what's important in the inputs, develop models for the inputs. Then we come to the classical uncertainty propagation. We propagate that thing through. And as both speakers before mentioned, Monte Carlo is one of the traditional things. We use Monte Carlo a lot. Sometimes we even go back to Taylor series and just do real basic stuff, because that's good enough, because the uncertainties in the inputs are far higher than any uncertainties in the method differences. So, and I just want to get an estimate, as long as you know what the assumptions are in here. There is advanced methods, so we use adjoint methods, principal component analysis, polynomial chaos, and some Bayesian stuff too, if we require to do these. So this is the basic process, and then you get an estimate for the uncertainty or the variability in your outputs. So just a few examples where we can highlight where we have applied that kind of process to some extent. So the first is, again, from the fan blade. So, and this is just a very simple one. So we manufacture these fan blades, and guess what? They are not according to the print. There is a tolerance on each of the dimensions. So we get around, this is the actual drawing, and these are all the sections where we measure things. So we're getting around 300 or 400 measurements per fan blade, locations. So we get this massive covariance structure here, which we just try to kind of plot here as a cross plot. So the other problem is, this is not what the aerodynamicists want. This is what the manufacturing wants. The manufacturing one just checks, where's my blade recording X, Y, Z. The aerodynamicist thinks in different parameters. He thinks in angles, he thinks in thicknesses, and so on. So you need to transfer that knowledge from manufacturing into a different space, different coordinate space, kind of, so that the aerodynamicist understands it. So that happens here. You analyze the data, you establish the correlations. You then do DOEs, so you can run quite a bit of number of points, as you can see here. And then you try to fit a response surface or surrogate model through these number of points. So that you then can do a Monte Carlo, similar to what you just explained earlier. So we fitted an emulator here. Just the equation was all that. And then we run the Monte Carlo on that to get in what's the efficiency, what's the weight, what's the cost for that component. So, and that component had around 300 inputs. So that was the first bit on my first slide, component level. So if we start to taking a little bit more uncertainty in, we get to that situation where we design our blade, we make it. That's what we have just looked at, kind of. We had a blade, and we looked at manufacturing tolerances. So if you do that properly, and I think you said it also, there's an accuracy in the finite element model. There's all these assumptions going into the finite element model. So what boundary conditions do I assume? What mesh and solver did I choose? We have even the problem, which design point do I choose? The engine runs at various speeds. Where do I design? At high speed, at low speed? Typically what we do is we design it for the most probable operating point, which is a cruise point. So all these designs are actually done in a running condition. So how do I get back from that running condition to the cold condition? So there's another uncertainty coming in. So there's a lot of things we need to tackle there. Geometric tolerances, assembly tolerances, how have the parts been assembled? What was the assembly process? Is the assembly process repeatable, and so on? And then the measurement side, when we measure these things, measurement uncertainty, test condition uncertainty, and so on. So, and to put that all together, we typically use what we call UQ studies, and that's what Ron and I are doing, kind of pulling all these things together and making a prediction of, given that, what do we expect the outcome of stress or life of that component be, given all these uncertainties. It's quite challenging sometimes. So, to make it even worse now, taking that one level up again, is doing that on a system level. There's an application we currently do where we actually go from the airline operations. So, because it seems that the airline operations affects how long these parts are lasting, which you can expect. So there's airlines who fly nicely around in benign areas, it's cool weather, it's nice. There's airlines on the military side where I'm working, we have the military. They're typically in very sandy environment, they get shot at, so these components last not that long than the civil components. So that operational profile affects things. We talked about environmental temperatures in sand, manufacturing data, material data we already covered in the earlier ones. But that's kind of the inputs going into that whole process. So there's a flight profile analysis which gives me how long is that part at certain conditions. There is a performance analysis which provides data to the downstream processes. So that's giving me how hot is the engine in the various conditions throughout the engine. Then there is an air system analysis which gives me the data about my cooling flows, how much cool air do I have throughout the engine. And then I have a component thermal analysis which gives me the information how hot is my metal given my operating conditions. And then I can do a stress and life analysis. And on each of these inputs, on each of the transfers, you have probably 10 to 15, if not more, uncertainties, and we treat them kind of separately because there's some of the knowns and unknowns, so aleatory and epistemic needs to be separated so that we can treat them properly. So these are the things we do with uncertainty quantification, with the methods you try to develop and you're developing. So you can use these things. A few points, I think, about some challenges we still have. So, as you have seen, there's typically complex multidisciplinary models. So what I mean is, it's all these disciplines going together, so it's not just a simple stress analysis, one tool, a set of boundary conditions, a set of results. These tools getting transferred to various disciplines. So, stress, thermals, geometry, the aerodynamics, impact, the vibration stuff, and all of these are contributing to a figure of merit. So it's not just the one figure of merit. So we have long-running simulations. It's all good if these things run quickly, but these typically take a day. These take 3 days, I think, to run one data point. You might get this in half a day, that might take a day. You're talking about a week maybe to get through that loop once. And then Monte Carlo comes and says, can you do me 1,000 runs? And then the analyst comes and shoots you. So no, I cannot do that. So that's where the advanced methods are required. So what can we do to get to the same answer with less runs? Circuit modeling, stochastic solvers, and so on. So this is one of the key challenges still. Do we have another one about, you can also see the parametrization is a problem typically. Each of the disciplines like their problem described in different spaces. So different inputs. It's all the same problem, but everybody looks at a different angle. Like you said earlier, oh, it's the same method, but we call it differently. The same thing happens here. It's the same part, but every discipline has found an ideal way for themselves to look at that same part, which now causes problems when you try to link them all together, because you do all these transformations of space in between. So, there, bless you. The example here is manufacturing looks simply in these lines. Aerodynamics looks like kind of what's the radii there, what's the curvature, what's the thickness. So equivalent descriptions but not the same. You have a lot of complex objectives. It would be easy to say we just need an engine which reduces fuel burn, good for the environment. It will be very heavy and very costly, will never fly. So you have weight restrictions, you have cost restrictions. So you need to balance all these attributes. That's why all these disciplines come in. So you need someone predicting the weight. Weight is relatively easy. Cost is more difficult, and so on. And a gas turbine has one big drawback in this respect. It's a very connected system. So you cannot really separate the systems because they all have so many correlations between them. So they're all hanging together. So we talked about the many sources of uncertainty. So the inputs are numerous on this problem. And there's big advantages or big advances now on the data analytics on the data side. So there's sensors now. You can get thousands of sensors on an engine. They can report every second if you want. So, but just imagine you have 1,000 planes flying around, and during the day, every second you get 1,000 data points. 24 hours, 1,000 data points coming in for probably 300 to 400 parameters per engine. That's an awful lot of data. So some areas you get a lot of data. Then the other stuff is you get sparse data. There is one of our planes in the US, and that's a typical operation if they go into war, kind of with landing on sandy strips. And as you might know, from your car engines, they don't like sandy environments and all sorts of things. So this is not good for the engine, so you want to know what's going in the engine. The problem you then will find is, the problems in the engine also depend on the type of sand. So now, is it sand from Saudi Arabia, or is it sand from Iraq, or is it sand from Afghanistan? So you see different problems. So now you need to collect that piece of data. So, and you don't have all that data, so you have big holes, despite the fact that there's all that massive data flow coming in. You might miss key points of the data stuff, and you need to deal with it. So these are the things which you encounter if you apply uncertainty quantification and so on in a real industrial environment. So as a summary, it's possible. We are doing these sorts of things. So we are doing it more and more. It can be applied to real business problems. It actually delivers business value, otherwise they wouldn't allow us to do it. If they would say, it's just nice and stuff you do, but you don't deliver value. So that's always the question, what does you bring to the party, kind of. It allows consideration of variation in the design process, and you can select nominal design. So you need to quantify the variation, and then that will drive your proper design selection. So as you've seen, there's challenges still available or for the more pervasive application of that. Data analysis and processing is one of the key topics. One of the key problems still is that integrated analysis I talked about, up and down that hierarchy chain. How can I transfer uncertainties up and down there? How can I manage that? And that multidisciplinary stuff, so that it's finite element coupled with CFD, coupled with cost, coupled with manufacturing, and so on. And I think that's the last slide I have. I don't know how many.
Thank you.
Any questions?
We have time for questions.
I will say who we are.
Sure.
Ian Mitchell, I'm from the Department for Business, Energy, Industrial Strategy. I'm very interested in the hierarchy of models you've mentioned. I've seen similar patterns in defence models, working up the scale from individual soldier models right up to formations of thousands of people. They had to be run 20 years ago when I was doing this at different levels because the processing power simply wasn't there to do more. I see similar problems now between different models within government, and I think there is similar questions about how do you transfer the outputs from one, which will become the inputs to the other on a fair basis. I don't know if you have anything to share on the social angles of this, because it's the models don't talk to each other, it's the people who run them who do, and as you said, quite often they have to find ways to translate.
Yes.
And so do you have anything further you could say on that?
So there's typically a lot of issues in that translation between the models and so on, because it's different domains, they don't talk to each other, they talk the same stuff. So one of the key things we typically try to do in this area is form that team across these boundaries. And you go through the typical team forming stuff, so it's more the storming first. And they clash and so on, but at some point they will start to work together and the boundary vanishes, so that works quite nicely. But it's more, like you said, it's more the people side, more the social side than the actual numerical side. From a numerical side, we can do that stuff. But getting then the team, the organization to actually do it is more a social problem, yes.
I think as well, I'm going to steal your quote now about, is it culture eats strategy for breakfast? Yeah. So there's a cultural side to it. And, we work in robust design, so our currencies, models, and data, and there's on the cultural side, we feel like if we make data more easily available and the methods to look at the data are more easily available, then people will kind of coalesce around that idea a little bit. And if you have a data-driven culture, that can also help that side of it, and coupled with the systems engineering side.
Yes. The data can be the backbone behind that hierarchy, so it's not models linked together, but it's the data structure behind it which links it all together.
A related remark actually to both of those comments is how the goal of doing uncertainty quantification would help shape the platform building that you're landing all of this data on.
Yeah.
So there's a lot of platform building going on now, but not very much in view of doing the uncertainty analysis.
Yes.
So it's very useful to think.
Yes, and that's a key problem. So they might build the wrong platform if they don't deal with the UQ problem, yes.
Most of the variables you've talked about are sort of standard variables, temperature and stuff, but I think you mentioned Afghanistan sand versus Iraqi sand. I mean, is that just about particle size or chemical? I mean, what sort of variable are you using?
Typically the variability there is chemical composition. So depending on the composition, it will have different effects in the engine. So you need to start, and now you're down to chemical composition of sand particles. And that's...
Sand will go liquid at some point.
Yes, so that depends. It gets kind of gooey when it's getting hot, and it's getting really hot in these engines. Then that's transition stuff is dependent on the composition. So some sand might be okay, some might not be okay, and now you have need to distinguish these two domains. So sometimes you need to dig really deep, and then but still have that system level view.
One last question.
Yeah, you used a couple of terms on one of your slides I'm not familiar with. Aleatory and epistemic uncertainty.
Yes, I don't like these terms there because one is the uncertainty, and I typically get them confused anyhow. So. One is a traditional uncertainty. You can put a probability against the probability distribution. So it's a real variability, things which vary in reality. The other one is an unknown, we typically call it. So there's a parameter like viscosity. For your fluid it's given, but you might not know it exactly. So you need to treat these two differently from a statistical standpoint.
Which one is which?
Epistemic is the lack of knowledge. So yes, the epistemic is the second one. And then I normally get them confused. That's why I've wrong.
The epistemic one is lack of knowledge that will become reducible as time goes on, as you learn more, while the aleatoric one is one that you live with and have to treat as being random.
Yes. So manufacturing tolerances would be the second one. So you cannot reduce it. It's just there. It's a real variability. Boundary condition uncertainty you can reduce by learning more.
Okay, thank you very much.